My name is Megan Gallagher. I'm a solutions engineer with Harris Geospatial Solutions, and today I'm going to be talking about using synthetic aperture radar to monitor subsidence that occurred in a case in Colorado where Highway 36 collapsed near actually our own office. So we will be going through the steps of using synthetic aperture radar to see if we could have seen this collapse long before it actually happened. So a little bit of background on the collapse itself. On July 12, 2019, a large crack began to spread across the eastbound lanes of the highway, as you can see from some of the images down below. And this was located near Church Ranch in Broomfield, Colorado. This highway butted right up against a dry lake bed that filled up during the wet season and also froze during the winter, so there was some connotations that there could have been some movement in this region, especially as Colorado is known for having collapsing clay. However, the next day, on July 13th, you can see that instead of a crack, there was a complete collapse of this highway. So what we're going to be doing is we're going to be using ENVI SARscape to see if we could have seen this crack before it happened and what mitigation, if there would have been time to do mitigation for this process. So when using SAR to track movement, there are two different methods that are used for long time series studies. The first is called persistent scatterers, or PS. The second is called small baseline subsets, or SBAS. PS can be used in cases that are showcasing linear behavior. Straight line, sliding down, subsidence that might occur, sinkhole perhaps. In areas of urban or non-urban regions that have, say a rock face, where they have persistent reflectors. What a persistent reflector is you are getting the same signal off of something. So say a house, maybe it's on top of something that's subsiding, moving down a cliff, what have you, but it is still the same house, so we're getting a persistent reflectance response from it. You need high coherence to get usable results with persistent scatterers. What that means is you need very similar images or very similar likeness between your images to get those usable results. SBAS can be used with nonlinear behavior. Maybe a quadratic or cubic motion has occurred instead. And it also can be used with those areas of lower coherence. Areas that are highly vegetated, such as forests or have dense grass growths, have very low coherence. So if you're looking at a scene that has this kind of thing, you most likely want to use SBAS instead. The Highway 36 movement had such low coherence that PS could not be used in this case, so we'll be going over SBAS for the rest of this. The SBAS processing that we use in ENVI SARscape is this chart as follows. We'll be going over these steps in detail, but one important thing to call out is the amount of imagery. So the first thing you need to do is import your images. When we're using SBAS or even PS, you want at least a year of imagery over a region or 30 to 60 images to build up that baseline for usable data. For this study in particular, 30 ascending track and 31 descending track Sentinel-1 images are used. What this is when SAR data is collected, it can go either ascending, so it's going up, or descending, or it's going down. What this means is that when we collect with SAR satellites, we are not looking directly down at the Earth. We are a non-nadir sensor. So as you can see from the images included in this slide, that means we get slightly different angles from our ascending and descending track. If we try to use this kind of process on just one side, so like only using ascending, we will only get imagery from the line of sight of the satellite itself, which will be explained more in the next slide. However, if we combine the two, we can get true vertical movement out of our images. Here's what I mean by satellite line of sight. Displacement with one axis in geometry is not that true vertical and horizontal movement. It is relative to the way that the satellite is looking at the ground. So for this example, if we have positive movement, that would be towards the satellite, and if we have negative movement, it would be away from the satellite. It is not up and down. After all our images have been collected, we can go on into the processing itself. The first step is what is called a connection graph. What this is it's showing the relations in between images on a temporal and positional baseline. We need our images to be similar enough that they can actually be compared to each other, and so that's what this is testing. It's pretty much saying whether we can do our processing or not. So here's some example of the connection graphs. If we look on the one on the right, what this one is showing us is every single green point is an image, and every single line in between them are the other images that it is similar enough to be connected to. A good connection graph should have 5 different connections for each point. You can see most of the ones in this example do fit that, though some of the ones on the bottom right do not. However, we have very good coverage otherwise, and every single one of those lines is going to be created into an interferogram, which is where most of the processing in this comes into play. Interferograms show the likeness of the phase in between the two different collects of the data. So this is done in between pairs and pairs and pairs and pairs of data until you get a stack of these rainbow-colored interferograms. An example is shown in that little SBAS interferometric process, and it has the rainbow colors there. So this phase is showing us what is changing in the scene in between those two images over time. And you do need to actually QA/QC these to make sure that your outputs aren't filled with noise. So these interferograms are generated, and once you want to QA/QC them for those unwrapping phase errors. What that is sometimes there's just errors in between the images when they're unwrapped. There might be noise caused by really strange atmospheric effects in the scene, or major changes, or just something may be wrong with the collect itself. And you want to remove those because you want your accuracy to be as high as possible. For this study, one SAR image was removed from both the ascending and descending tracks because of the noise it caused. The next step is refinement and flattening, and that uses ground control points to find movement in your scene. You can either have these points collected out in the field, or you can also do them in the program itself. These ground control points need to overlap in every single scene, so sometimes you need a lot of them if you have a very low coherent area. These ground control points are showing relative movement. You're saying that this is where it is stable, and the other areas are the areas that it moved. So these are really important for the processing. After that, we have the first inversion. This will also be another one of those little bit of a longer processing steps. And this calculates the residual phase and displacement to reflatten the phase and generate better products. You can think of it as a cleanup step and something that is preparing all of our images to actually be put into a model. After that is the secondary inversion. And what this inversion does is something that we don't usually get to say in remote sensing, but it removes atmospheric effects. Because we have so many images, and because synthetic aperture radar is an active system, meaning it is not usually affected by clouds, rain, maybe a little bit snow sometimes, but because it is not usually affected by weather, we have very specific ways to remove the atmospheric effects from our scenes. And lastly, it will fit the output to the displacement velocity model, which cubic, bicubic, linear, quadratic, etc. We are now seeing how this movement of this area is changing over time. So here is a line of sight movement of this region, and I should let it be stated that you also need to geocode your imagery afterwards, because when you're collecting from satellite line of sight, it can be upside down and backwards, and so it will be geocoded to be georeferenced to the proper frame of reference. This slide is showing the ascending geometry displacement shown in vector files, which all of these points are. What all these points also hold that you can go out and look at in SARscape is the time series of movement. So as you can see from the chart on the right, which is very dramatic looking towards the end of the chart itself. Here we have Broomfield, Colorado. The area that is circled is Highway 36. The area that has the little blue points in there is the area that collapsed. You'll also notice some other areas of interest where we're seeing large movement. To the north, we're seeing a lot of blue. From my look in that region, there was some excavation that was occurring. However, a little bit south of that open region, that is the lake bed that was right next to the highway, as you can see. Water has very, very, very low coherence, and so it is usually masked out of any kind of SAR processing unless you're specifically looking at water, such as shift detection. But we can also see along the southern face of that lake bed, there's also a lot of movement there as well. Let it be noted, there is a train track that goes through that region, so something to take a look at in the future, I believe. So the movement is seen in the satellite line of sight, but that doesn't mean we can't see these major areas of movement, and if we track those changes over time, we can see some very interesting things. Mainly, we have so many images, we can see this stable baseline in that chart right up until it hits about May of 2019, and then there is a dramatic descending movement away from the satellite itself into that lake bed. And May is a couple months before the actual collapse happened. So we're getting some positive results there. Here is the vertical movement. So this is using both the ascending and descending tracks of the satellite to get that vertical change that occurred. And I've chosen 3 different areas to highlight the movement in this scene. The first, as you can see in the top middle-ish, is over that area that's showing a lot of movement that was mainly having to do with the excavation that was occurring. The one that you might not be able to see as well is directly on the highway itself. So if you look at the chart, the movement on the top is the red line, the one that is the highway itself is the lime green line, and the one that is this green area in the sort of middle right is a darker green line. And we can look from the chart to see those major areas that are moving. Very interestingly, the Highway 36 and the major movement do match pretty well on when they occurred, so I might need to go double check that one again to see if the excavation started at the same time. But for the highway, once again, we can see it's late August, May that we get this major downturn in the highway itself into the lake bed. The stable area remains relatively stable throughout this entire period, which is a good thing, as that is where a lot of buildings are located. One of the last things we always like to check is vertical and horizontal movement over this region. This is over that point on the highway where the collapse occurred. We have here in this chart both horizontal and vertical movement matched over time. Within the timeline that we have, the area around the highway that was moving to that Churchill Lake, it was moving there horizontally continually. So as such, to really pull out any information from that, we would need to increase our baseline to see if this was normal movement or if it has just been moving since the highway was made in that area into the lake bed itself. Some areas, the earth moves, it can move naturally, so we can't really say too much on whether that is a natural or unnatural effect that occurred. The vertical movement, however, has a very obvious change, occurs around late May. I was checking this against the weather, and in late May we had a lot of rain. In that case, the day before, or a little bit before the day before this happened, we had about 4 inches of rain in one day, and we had periods of extremely high temperatures and extremely low temperatures, all things that commonly cause the clays in this region to collapse. This is the monitoring. According to this, if we had been tracking some of the vertical movement, we might have been able to capture this movement, especially in that massive degradation down into the lake bed around May, in time to prep for the possible collapse in July. Alright, with that, my time is up. If you have any questions, please feel free to email me. Have a fantastic day.